coming up. The company is Electron, and I'm really happy to introduce Michael, the CTO, on stage. Electron is a spin-off of the University of Siegen. They already managed to get two big business things from the DLR, from the aerospace, German Aerospace Center. So their quantum chip is in Hamburg and also in Siegen. And what you guys are planning to do, he'll introduce us to magic quantum computing for industrial benefits. And I would say, Michael, with this, stage is yours. Please, have an applause.
Yeah, thanks a lot for the nice introduction. What I'm going to do, yeah, same problem maybe again. What I'm going to do is a bit, explaining the platform IONS here, because it was not so heavily, on the stage so far, and to explain our way to implement it for industrial applications. Are we good? Not the wrong. And when I'm presenting, I'm basically not only presenting the results of Electron, because we have a strong connection to the chair, thank you, thanks a lot, of the experimental quantum optics group at the University of Siegen, where we are a spin-off from. So this is basically a joint effort here. I'm not going to say much why quantum computing. Everyone who is here knows that already a lot. So there are many, many ways to apply quantum technology, quantum computing, and I think the visions are so large. One thing I like a lot is actually to think that certain things we are used to, like medicine, that pharmaceutics are just made for the society in general, can be completely turned around, and you could have like an individual medicine where you get your individual drug that has knows your genetic code and is just for you, and so certain things would work completely different. So I think why IONS is a valid question, because we have many, many quantum systems here, and since we are still lacking like the number how to assess everything at once, you could sell different systems as very promising, and there are a few, but it's difficult to really figure out what is the best. So what is good about IONS? So one thing that you might be tempted to is just count qubits, and actually when people visit our booth, that is often the first question: how many qubits do you have, and when do you have a million? Huh? And that's a difficult question. For IONS, that's a bit intimidating, actually. But qubits are not everything. And it's also a bad number if you talk about physical qubits, because in the end, you all expect that you need logical ones. And if you now think there is an overhead to that, you basically need to divide by that overhead of what you really have. And if you do that, well, then every platform is on the order of 1. So that sounds completely different now. There's reliability. And what we all need to do, and it's a challenge for everyone, is to scale our systems that work for a few qubits to many. And actually, it's from making a tiny Schrödinger kitten a big cat. And that is not going to be easy for anyone, that's certain. And when you scale up, the question is, will you experience new things that you didn't expect before? That is bad scaling. You want to have something that you know exactly, and it just is copy and paste. That would be ideal. Let's see. And then speed, of course, right? I mean, we are making computers. We want a result. So before I explain our system, I'm just saying what is nice about it. So atomic qubits are just made by nature. Their properties are given by the laws of nature, and they are the same everywhere, and the qubits are the same everywhere. And if you look what makes a good qubit, or what makes a good reference oscillator to trigger your time base, it's pretty much the same thing. So the best clocks in the world are atomic clocks. Atoms make really good qubits. You want to have your system having fairly low technical overhead. I mean, the simpler the better. I mean, every component is a resource for problems. Cooling is pretty easy, well, for me, and for the community that is used to that. So we do not need cryostats. Our first machines work completely at room temperature. Just the atoms that we use are cold. And we talk about 10, right? I mean, to cool 10 atoms is easy. To cool a kilogram of copper is not so easy. Yeah? We have all-to-all connectivity. So all the ions are charged, they repel each other, so they talk to each other. So basically, that can be a resource to implement algorithms more efficiently. And future-proof, so what is good about ions, it's not our result, it's the result of others, is that ions have been shown to implement quantum error correction in a way that is beneficial. So you do things, additional gates, measurements, and so on, each comes with an error, and then you correct maybe something, again with an error. So the overall thing needs to be making it better. And so that's actually not so easy, and with ions that has been shown. And what you want to keep an ion in a place is a force field that keeps you at a point, and if you now dislocate, it brings you back. That's what we want. Okay, so that's our wish list basically. So it means basically you get stability. And you could also have a picture of a bowl in which an ion is sitting at the bottom, and you could think of a depth. And the depth of ion traps is pretty large. You could put it in terms of temperature, and the depth can have a temperature that is much, much higher than room temperature, meaning that if you let it warm up to room temperature, it still doesn't escape out of the bowl. That's nice. And we do this because you can't directly do this with just some DC fields with RF electric fields. Ideally, you need some electrodes which would be hyperbolic, which is really difficult to machine, but it turns out you don't need to. You can actually even use square boxes, connected to some cables. The world is not 2D, it's 3D, so these boxes should really be boxes. And then you need probably not just 4 of them, but maybe many. And I'll say that in a minute for what that is fine. So that's called segmentation. And then you can apply this RF field, appropriate DC potentials, and then you can trap ions, and they form, if you put the parameters right, into linear strings. And you can then apply laser cooling. That's the only place, except state detection, where we use lasers. And then you can make photos, and I'm still amazed that you can just make a picture of a few single atoms. And it is, so I hope you can see that here. So here, these 4 dots are 4 atoms, and you can just photograph them. And you can take more, and then you get longer strings. And this is a register for quantum information. And if you make it even longer, you see now that it gets like a zigzag structure. That's exactly how it's called in the literature. Yes, and you lose this 1D property, but you could still even use that. Our concept is called magic, so that sounds nice, but what is it about? It's not just a nice word. So what do we want for this quantum computer? We want to have a good control on individual qubits. We want to have a platform where we make some building block and just step and repeat it. So integration is absolutely essential. And integration without compromising performance. No bad surprises, please. So what is good about magic here, before I explain it again, the other way around, is when we want to talk to a single atom and not to any else, we talk to a single atom and not to any else. So we have the world record in low crosstalk, and this world record is pretty much 10 years old, so it seems difficult to beat. So that's maybe nice. Single qubit gates can be done with pretty high success rate. So what we achieved is 99.96. That's already pretty good and makes it quite an effort to measure the error, because it happens so rarely. The world record with microwave-based gates has even 2 more 9s. So if you really go for it, you can make it really good. Oh, sorry, I went accidentally forward. Microwaves is something you have in your smartphone. So I don't need to prove that it integrates really well, that you can make it miniaturized. You can make antenna, amplifiers, phase modulation, whatever. It's all in your pocket. And the lasers that we are using, we just use them for cooling and for detection. which is all actually fairly easy and you can just buy it. So what's our qubit like? We think of it as being a tiny magnet, something with a magnetic moment. And if you expose it to a magnetic field, it would align itself, and that's what you're used to. Now, if you would take this magnetic needle and rotate it, you would need to work against some force and put energy into it. And to rotate it by 180 degrees, you put in some energy. That's the second energy level. Classically, you can have any orientation. Quantum mechanically, you just measure this or the other. Okay, and the energy gap is given by an energy. You could also express it by a frequency, and the good thing about that expression is it tells you what frequency do I need to put in to change my single qubit. So you can even change it by changing the magnetic field strength. And that's what we now use. So when I now have 2 qubits in my bowl, in my trap, and I make the magnetic field inhomogeneous, so it gets stronger towards the right, this qubit splitting is a bit different for the 2 qubits, and it looks like this. So each qubit has its own transition frequency, and we make single qubit operations by just dialing in the right frequency. And so this is the proof of that. So the very sharp peaks are resonances in the absorption spectrum. And this is really centimeter wavelength radiation, whereas the upper picture is a photo, so with nanometer or sub-micrometer radiation, and you see even that the needles are much, much sharper in the RF spectrum. What you also want is that the qubits talk to each other. They repel each other, fine, but you need also something to convert between this internal state, what is the direction of the needle, to where it sits or how does my ion move around. So how does that work? Basically, what we created here is a spin or state-dependent force. If I have the situation as before, you see that in the lower state, I feel like I should be sliding towards the right. So if I put one ion here, it's completely exaggerated, just for clarity. I wouldn't sit at the very bottom of the potential, but a bit shifted to the right. And now I make a single qubit gate. I move to the upper state, and all of a sudden I feel a sliding force to the left. And now my equilibrium position would change. And that's what we call magnetic gradient-induced coupling, for short, MAGIC. So this coupling is only due to the gradient, and actually if one ion slides, and there would be more ions, they would also notice, oh, I'm also sliding because of Coulomb repulsion. Actually, when you want to turn that into a gate, we figured that there are at least 3 ways to do that. One would be to do like NMR, like spectroscopy. It's what we've done the longest time now. It works pretty well. We have high fidelity and so on. It's pretty established. We can use dressed states. That just means that you take into account the effect of the microwave signal into your steady state calculation. Or you make a modulation of your microwave signals, and that corresponds actually to the physics that other people use when they use lasers. Every has its pros and cons, and this actually is a picture of the first quantum computer in Germany. It stands in Siegen. Look it up on the map, so probably you don't know it. So it works now for 10 years. At least if you say something with a few qubits where I can run algorithms is a computer, and that's what we can do here. We did the quantum Fourier transform, and we did small quantum enhanced machine learning algorithms. Now, when we want to get this to the point that we can do anything for any customer, we need to get a lot bigger somehow. Well, bigger in terms of specs, not in terms of size, of course. And that means we need to scale our system down. So basically, you saw the machine before. It didn't even look like a computer. It was filling 3 square meters of an optical table, several racks of electronics. And this doesn't scale, right? You cannot just multiply that with 100 and have now 200 racks of electronics. That's not working. So you need to get the electronics close to the chip and on the size comparable to that chip. So when we talk about integration, we talk about first integrating qubit control. That can be making DC sources, making maybe an RF source the microwave signals that change the qubit, all that. And we have many, many projects in which we do that. For example, partially at the chair, the QMIC collaboration does exactly this, qubit control integration. Optical integration is, for example, done in the ATIC project. Photonics, so detectors are integrated in the QC project with the DLR, and so on and so on. So why do we believe we are worth a thought here? So, okay, the price is already some nice reward so that others think the same. So this is our timeline. So the idea actually was done in 2001. We demonstrated the building blocks at the chair and then figured that actually we can't get any further in the direction of a product at the chair. So certain strategic things work better in a company, and we founded Electron in 2020. And since then, it has grown to now 40 people roughly. So we are at 2 locations in Hamburg and in Siegen. We acquired venture capital, which allows us to start funded projects, several very large ones here, and we were able to sell 2 machines to DLR, and more are in the pipeline. Another thing that maybe is a good way to, we feel we run it, is that we have from the beginning a pretty strong competence in economy here and how to run something and how to scale a company, not a quantum computer. So because that's actually quite some point here. And Jan Leise has a huge expertise in these things and actually is a nice driving force when it comes to how to form a team, how to make processes and so on. I think we are pretty professional here. Christoph Wunderlich is the guy with the science and the network, and my job is to bring the technology development further. And last but not least, I think we have really an awesome team, and for us it was actually some experience to figure out that we shouldn't look out for generalists as we ourselves in some sense were, knowing everything a little, but we now actually have really excellent specialists on individual topics here. And yeah, these are really nice people, and I think we are probably the only quantum company where pretty much everyone has a sailing license. So, okay, yeah, thanks for your attention.
Thank you, Michael. And maybe I think we have time for one quick question. If there's one quick question in the room, then I would give time for that. Daniel.
Yeah, thanks, Michael. I have to say, every time I listen to that talk, it's still getting me more and more excited. Haha, funny joke about excitement. You'd mentioned about the team. How are you have something that is more like on a strategic management level, potentially, is like skilled labor? How do you figure at Electron going on? What is in terms of human resources? What is the English word like people coming? 15 nations. That it's amazing. It's an international topic.
Yes.
But do you feel that there is a need for more young people? I saw many young people coming out of that amazing truck there. Maybe you can comment on that.
Yes. So, I mean, what we acquired a lot of people is from other countries, because in Germany there are frankly not enough. But so far that has not caused any problems. I would say the team spirit is really there, even though the different cultural backgrounds. What we do have is actually in Siegen we start a new master's degree of quantum science, and actually I think that's a good program that could start in several places to really get the expertise for the next generation. I think that's really a demand.
Thank you, Michael. Thanks for being here.